All right, hello and welcome back. We are getting started with Chapter 8. Okay, so this is Chapter 8. This is something that we normally would have done in first semester, but time problems caused us to have to push this into second semester. This is sort of a different take on what we were doing at the end of first semester. First semester, we ended with Chapter 7, which was on ionic bonding and metallic bonding, where we talked about the reasons why two atoms, a metal and a nonmetal, would come together. And that's because the metal would like to lose its electrons. The nonmetal wants to gain its electrons. The metal becomes positive, the nonmetal becomes negative, and then there's an attraction between the positive and negative, and that's what pulls them together. Well, this kind of bonding, covalent bonding, is a lot different than that. Okay. So in this chapter, in Chapter 8, we're going to be talking about nonmetals and other nonmetals coming together. So nonmetal bonding is what we're doing here. So this chapter happens to be a little bit more extensive, and we have a little bit more to go through in this chapter. So let's get started with what we're talking about with covalent compounds, right? So, like I said just a moment ago, covalent compounds, covalent bonding occurs between a nonmetal and another nonmetal. Now, they couldn't bond ionically. That wouldn't make any sense, right? Because nonmetals want to gain electrons. But if there's only other nonmetals around, what are they going to gain electrons from, right? If everybody's looking to gain and nobody wants to lose, there's nothing to gain. So they can't bond with each other ionically. So if nonmetals are going to bond to each other and get their octet, all right, you got to kind of search back through your brain pre-holiday break, right? And you got to think about, what did we learn about octet rule? And that was that all elements out there, all the atoms, want to have 8 valence electrons. That's what makes them very stable. And the only elements out there that naturally have 8 are the noble gases. And all the other elements are constantly trying to find a way to get 8. So the only way that nonmetals can do that is either they have to gain some electrons from a metal, or they're going to have to share electrons with another nonmetal, which is what we're talking about here. So that's what forms a covalent bond. They're going to share their valence electrons. So the co means together, right? Sharing. Valent means valence, which is the valence electrons on the outside. So let's take a really, really simple example of this. Now, these are 2 hydrogen atoms. How can we tell that they're hydrogen? Well, in the picture, we only see 1 proton, 1 positive in the nucleus, and we only see 1 negative electron. So all hydrogen atoms have 1 proton, and they have 1 electron. Now, remember, a hydrogen wants to be like its nearest noble gas, which is helium, and helium only has 2 valence electrons. And if you remember, it's because hydrogen and helium are both in that first period on the periodic table. They only have a first energy level, which is just a 1s. So once their 1s is filled, they would be very stable. So hydrogen is looking to get 2 valence electrons. Now again, if there were something out there that would just give it an electron, it would be pretty happy with that. But there isn't. There is just another hydrogen who's also looking to gain. So if both of these want to gain 1 electron and neither one of them is willing to give up the electron to the other, then that means they're going to have to share. So if they were to share, they would first of all have to come a lot closer together than they are in this picture here. And so if they got closer together, their 2 electrons could sort of overlap. And now this atom of hydrogen here can claim that it has 2 valence electrons. This atom here can claim it has 2 valence electrons, and they're both pretty happy. But to stay that way, they have to stay together. If they were to come apart, then each of them would only have 1 valence electron, and they would no longer be stable. So that's what covalent bonding is all about. Okay? Now, when we're talking about covalent bonded molecules, right, then we use the term molecules. We didn't use the term molecules when we were talking about ionic and metallic, because technically when they come together with positives and negatives like they did there, we're not technically forming molecules. But here we are. And so we tend to call these covalent compounds, we call them molecular compounds because they're forming molecules. And they have molecular formulas. Now, these molecular formulas look a lot like ionic formulas. The difference is that these are all nonmetals in these formulas. Okay, there's no metal at the beginning of these. One other thing that I want you to remember here is that there are a number of elements on the periodic table that naturally will share electrons with itself. In fact, 2 of the atoms of each of these elements will always come together if there's nothing else out there to bond with. So hydrogen and nitrogen and oxygen and fluorine and chlorine and bromine and iodine are the 7 elements in the periodic table that always form diatomic molecules with themselves. So now, why is that important? That's important because if we were to write the formula for any of these 7 elements, and notice it's really easy to remember because the NOFClBri part of this looks like a number 7. I know there's an H over here that's also part of that. But the reason why that's important is because anytime we write the formulas for those, we have to write them as something 2. So if I were to say write the chemical formula for oxygen, you're not going to write O. You're going to write O2. If I said write the chemical formula for bromine, you're going to write Br. You're going to write Br2. That's because each of those, and only these 7 elements, form diatomic molecules with themselves. So that's something to keep in mind when we're writing out chemical formulas. And we're going to be doing this for the rest of this semester, the rest of the year. Okay, so what do we know about molecular compounds compared to those ionic compounds? You remember ionic compounds had some properties that we learned. Ionic compounds are always solids, crystalline solids. Ionic compounds have really high melting points, right? Because their ionic bonds are so strong, hold them together. And if you dissolve an ionic compound in water, it will conduct electricity, right? Those were 3 things that we learned about ionic compounds. Covalent compounds are very different. Okay? Covalent bonds are not necessarily as strong. The difference is that covalent bonds only hold together individual atoms. They do not hold the whole structure together like an ionic bond would. Let me kind of show you an example of this. Okay? If Na and Cl wanted to get together, they could do that because Na is a metal. It likes to lose an electron. Cl is non-metal. It likes to gain an electron. So Na would give its electron to Cl. Na then becomes positively charged. Cl becomes negatively charged. And then they come together because a positive and negative always attracts, right? And then another positive and another negative and another positive, another negative, another positive. Notice that the whole structure is being held together with positives and negatives. This is all ionic bonding holding that together. But let's say that we wanted a Cl and a Br to come together. Now they're both nonmetals. So the only way that they could come together is they would have to share their electrons with each other. But once they're sharing with each other, what attraction would they have for any other one of these Cl-Br molecules? Not necessarily anything. We're going to learn that there are some forces that may hold them together, but those intermolecular forces are highly variable. That means that they're not consistently strong like all of these ionic bonds are here. So ionic compounds are always going to be solids with a really high melting point. But molecular compounds could be lots of different things. They might be gases. There might not be much force holding them together. They could be liquids. They could be solids. They could have a high melting point, but a lot of times they won't have a high melting point. Water is a good example of a molecular compound. It has covalent bonds holding the water molecules together. Okay, so the actual molecule is being held together with covalent bonds. The hydrogens and that oxygen are being held together by sharing electrons with each other. But what holds the actual molecules in between together? Well, those are called intermolecular forces. Those intermolecular forces aren't necessarily as strong as ionic bonds, and therefore water a lot of times, at least at the temperatures that we know it as, right? Water a lot of times is a liquid, right? But salt is an ionic compound. Salt is being held together with ionic bonds. All the way through, every bit of this is held together. So salt is always found as a solid, right? Water can be a solid if you get it cold enough. It can be a gas if you get it hot enough. You can do those things to salt, right? You could get salt to turn into a liquid or a gas, but it would take ridiculously high temperatures that we would never have at our disposal on a daily basis. But water, we've seen it in all three forms all the time, right? Because it's not hard to go between those. So again, we're going to talk more about these intermolecular forces near the end of this chapter. But for now, right, the important thing is to realize that there is a big difference between covalent compounds made up of just nonmetals, where they're sharing their electrons, and ionic compounds, where there's that give and take, there's a transfer of electrons, and they're being held together with those positives and negatives. All right, let's go back to this idea of covalent bonding. You saw that example before where we used two hydrogens, and we were showing that. Let's use something that we learned back in chapter 7. And remember, we learned how to draw dot structures. So here's what I want you to do. Okay? I want you to draw the dot structure for hydrogen. Now, how are you going to do that? Well, you're going to need, obviously, a couple things. You already have your paper and pencil, so you're already writing this down. But you're also going to need a periodic table. Right? So if you've got your periodic table available, you need to be looking at that. You need to determine where hydrogen is on the periodic table. What group is it in? And of course, you can see that it's in group 1. And that means that it has one valence electron. So it needs one dot. So we need to draw one dot next to hydrogen. Now we're going to do the same thing for the other hydrogen. So again, both of those hydrogens have one valence electron. How many do they want to have? Well, they want to be like their nearest noble gas. And nearest noble gas to hydrogen is helium. Helium only has 2 valence electrons, so hydrogen wants 2. So again, what can this hydrogen do? Well, it can share this one electron with this hydrogen, and this electron could be shared with that hydrogen, and they could share these 2 and be perfectly happy. But to do that, they're going to have to get closer together. So we take those 2, and now we put them in the middle as we bring those hydrogens closer together. So we took a hydrogen atom and another hydrogen atom, and we brought them together to form a diatomic hydrogen molecule, right? Di means 2, atomic means 2 atoms, right? So 2 atoms together, and those 2 electrons right here are being shared. Okay, that's our shared pair of electrons between the 2. That's what's holding them together. There are no positives and negatives that are holding together this time. It is simply the fact that they're sharing their electrons, so they have to stay close together. So one shared pair of electrons forms what we call a single covalent bond. All right, now hydrogen obviously is the simplest of all examples. Let's just jump up slightly. Let's try to do this with fluorines. So again, you're going to need your periodic table. So I want you to look at your periodic table. I want you to find fluorine on your periodic table. Pause this if you need to, right? Don't just wait for me to say everything in the notes. If you participate, it's a lot more interesting for you, and you're going to learn a lot more than just me saying it to you. All right, did you find fluorine? What group is it in? It's in group 17. So that means it has 7 valence electrons, right? So for the fluorine, we need to draw 7 dots. Remember, when we draw dot structures, we only put 2 electrons on each side, no more than 2. So we're going to do the same thing for the other fluorine. So there's another fluorine here, so we need 7 also. Now, how many does fluorine want to have? Well, the nearest noble gas to fluorine is neon. Neon's right next to it on the periodic table. Neon has 8 valence electrons. So fluorine wants to have 8 also to be stable. Well, it's only got 7. What would it love? It would love if something would just give it an extra electron. But there's no metals here to just give it an electron. So what if this fluorine took this one single electron that's right here, and this fluorine took this one single electron that's right here, and they shared those two? If they did that, obviously they're going to have to get closer together to share. So we draw them closer together, and let's draw now all those same electrons again that we had from before. But we notice that the 2 that were single now form a pair right in the middle. There's our single covalent bond that holds those 2 fluorines together. Now, I don't want to get confused because you notice there's a number of electrons here that are not being shared, right? That are not between the 2. And I don't want to get confused between the electrons that are being shared and the electrons that are not being shared. So here's what we're going to do. From now on, anytime that we share electrons like this, we're going to replace those dots with a dash. So all of the electrons that are not being shared stay as dots. Okay? But the electrons that are being shared, we're going to put a dash there. All right? So this is the rule from now on. We don't draw our shared pairs of electrons as dots anymore. Anytime that they're being shared, we're going to replace that with a dash. That dash still stands for 2 electrons, but those 2 electrons are being shared. So there's our single covalent bond. Now, what about all of these other electrons here? What about all the other pairs of electrons that are not being shared? Well, they also have a name, right? All of those are called lone pairs. So lone pairs are pairs of electrons that the atom has but is not sharing. Hydrogen didn't have any of those because it only had 1 electron to begin with. So it didn't have any extra electrons that it wasn't sharing. But fluorine has quite a few that it's not sharing. All right? Just don't forget, this is just a little reminder here. This is something that we've talked about before. But when you're drawing dot structures, don't forget you're starting with 1 dot on each side before you start going to put in 2 on each side. Okay? Now, we know that from ionic bonding, we didn't always have to have just 1 of each of the elements. Like, for instance, if we put magnesium and chlorine together, magnesium is positive 2, chlorine's negative 1. That means I needed 2 chlorines to go with the magnesium. Well, just like ionic bonds, covalent bonding sometimes takes more than 1 of each atom to complete it. So, for instance, water. There's a reason water is H2O. Why there's 2 H's with the O. Why is that? Well, the way that we can figure that out is let's draw out the dot structures. So again, hydrogen, look it up on the periodic table. What group is it in? It's in group 1. Therefore, it has 1 valence electron, so it has 1 dot. Oxygen, look that one up and draw that one for me. Okay, so you drew oxygen hopefully by now. If you haven't, pause and do it and come back. So oxygen has 6 because it's in group 16. So we need to draw 6 of those. And again, remember, we start with 1 here, and then 2, and then 3, and then 4. And then we just start putting 2 on each side once we have 4 of them around, right? All right. So what do we know about this? First of all, we know that hydrogen always likes to have 2, right? Because it likes to be like its nearest noble gas, which is helium. Helium only has 2. Hydrogen wants 2. So this hydrogen wants to have 2. It only has 1. Oxygen has 6. It wants to be like its nearest noble gas, which is neon. Neon has 8, so it wants 8. So, well, we could do this is anytime we see single, already not paired electrons, they could be shared, right? So these 2 right here could be shared. These 2 right here could be shared. And everybody could get what they want, right? Because now the hydrogen could claim these 2. This hydrogen could claim these 2. And this oxygen could claim all of these since it's sharing all of these, and that would be 8. So we got to put them sort of closer together, right? So I'm going to put this hydrogen closer to this electron here. I'm going to put this hydrogen closer to this electron here. And so notice this hydrogen's got 2, it's happy. This hydrogen has 2, it's happy. This oxygen has 8 around it, it's happy. But of course, these 2 and these 2 are both being shared. And what did we just learn about shared pairs of electrons? Shared pairs of electrons need to be turned into dashes. So let's redraw this one more time, but this time let's put those dashes in. So this is a single covalent bond here. This is a single covalent bond here. So why is water H2O? Because that's the only way that the sharing would have resulted in everybody getting what they want. Right? Oxygen wanted 8, hydrogen wanted 2. It's the only way this was going to work. And there's our water molecule. Now notice that oxygen still has 2 lone pairs that it's not sharing. Okay. All right, here's what I want you to do. Just like we did there, just like we did with the water, I want you to try 2 more on your own. I want you to try drawing the structure for NH3 and then draw it for CH4. What are you going to have to do for each of these? You're going to have to start by drawing an N and 3 H's and draw all of their dot structures separately. And then I want you to figure out where the sharing can occur. And then I want you to eventually end up with a structure that looks like this with the dashes put in. So try that for NH3 and for CH4 on your paper right now. Again, try to do this. Don't just ignore this. Don't just put it on autoplay and go do something else. You need to try to do this. It's the only way you're going to learn how to do this. Okay. I really hope that you've gotten this figured out. Even if you struggled with it, it's better to try it yourself than to just watch me do it. Okay, that's really super important. All right, for NH3, right, we would have started out with 3 H's. Each H only has 1 valence electron. How do I know that? Because they're in group 1. And the N, the nitrogen, started off with 5. Again, how do I know that? Because I looked up N on the periodic table. It's in group 15. Therefore, N has 5. So, how many do the hydrogens want to have? They always want to have 2. How many does the nitrogen want to have? It wants to have 8. And notice that it looks pretty clear as to where the sharing can occur. Anytime there are single electrons, they can be shared. So there's sharing that can occur here, between these 2 here, between these 2 here. And so we redraw it by sharing those and those and those, and we get 3 dashes. We still have this lone pair here. How do we know that this worked? We know this worked because everybody should get what they want. Does the hydrogen want 2? Yes. Does it have 2? Yes. This hydrogen has 2. This hydrogen has 2. This nitrogen wanted 8. It has 2 here, plus 2 from this dash, 2 from this dash, 2 from this dash. That makes 8 total. For the CH4, you needed to draw a C and 4 H's separately. The C here in the middle has 4 valence electrons because it's in group 14. How many does it want to have? It wants to have 8. So notice that this hydrogen here is going to share here. This one's going to share here. This one's going to share here. This one's going to share here. And so there are 4 covalent bonds that form in this structure. Every hydrogen has the 2 that it wants. And the carbon here in the middle wanted 8. It has 2, 4, 6, 8. Okay? So this process here is the basic idea of how we share electrons. This is what I want you to spend some time doing, looking through your homework problems and making sure that you're doing at least some of the basic ones. Okay? And then we'll go through, in the next lecture, we'll go through a slightly better way of doing this. Because, as you might see, this could get kind of confusing if we started using much more, many more atoms than we have now. Well, let's say that we had a much bigger formula than just CH4 or NH3 or H2O. Things could get a little bit crazy here. Oh, one more thing. I wanted to point this out. Sorry, one more thing. We can have more than one pair being shared at a time. Right? Anytime that you're sharing 2 pairs of electrons, that would be a double covalent bond. If you share 3 pairs of electrons, that would be a triple covalent bond. There's no such thing as a quadruple covalent bond. Please don't ever try to draw one. Okay? It doesn't exist. But double and triple can exist. So I do want to show you one example of each of those before we end this. Let's try to do this with oxygen. So again, look up oxygen on your periodic table. Oxygen is in group 16, right? So it's in group 16, so it has 6 valence electrons. So we need to draw 6 around it. We're going to do the same thing for the other oxygen. Okay, now, where does the sharing occur? If they were to simply just share these 2 electrons right here, then they would both end up with 7. And that wouldn't make them very happy. They need 8. So not only are they going to share these 2 right here, but they're also going to share these 2 here. And so if there's 2 places where sharing is going to occur, then there are 2 pairs that are being shared. Right? Right here in the middle, there's 2 pairs that are being shared. And we're going to replace each of those shared pairs with a dash. And so there's 2 dashes that occur between those oxygens. So we took and we made a diatomic oxygen molecule with a double bond in it. This is how oxygen molecules, the ones that you're currently breathing right as this is being said, right? The oxygen molecules that you're taking into your lungs right now, this is what they look like. Now, why did I draw these lone pairs at angles like this? Why didn't I keep them like they were over here? We'll eventually learn why I did that. Right now, if you didn't, that's not a big deal. Okay? We'll get there. You'll eventually learn why we did that. But for now, it wouldn't have been a big deal. Now, the other part of the air that you're breathing, in fact, the much larger part of the air that you're breathing, is nitrogen. Okay? And nitrogen is also a diatomic molecule. That means that it likes to pair with itself. But to do so, it's going to have to do something even more dramatic. Now, where's nitrogen on the periodic table? Group 15, right? So it's in group 15, so it has 5 valence electrons. So this nitrogen has 5, this nitrogen has 5. They have to share. But how are they going to get their 8? Well, they can't share just 1 time. That would be 6. They can't just share 2 times. That would be 7. They're going to have to share all 3 times here to get 8. So sharing here, sharing here, sharing here. So that means you're going to have 3 pairs that are being shared. We're going to replace each pair with a dash And so there is a triple bond that occurs in a nitrogen molecule. Okay? So, again, I want you to look through your problems in your homework and start working on some of these. Practice doing some of these. But in the next lecture, I am going to show you a much more foolproof way of doing these structures that we're drawing. Okay?